Welcome to section 1.4. We are talking about exponential functions in this section, looking at their basic form, looking at them graphically. So to start off, we're going to introduce what does an exponential function actually look like. The general form of an exponential function is going to be b to the x, where b is the base of the exponential function, and we can make a note here that the base b dictates the shape of the graph. So the value of b is going to determine specifically what this graph looks like. Now, they all have a general shape that they obey, but if we look at, for example, a couple different bases, here we have the red graph is the graph of f of x equals 2 to the x. So you can see here we have 2 to the 0 is 1, 2 to the 1 is 2 right there. 2 to the 2 squared is 4. 2 cubed is 8, and that's heading on up there. 2 to the negative 1, so that's like, 1/2 right there. So you can see some of these major points. If we were point plotting, it would give us a shape that looks like this. If you take the base to be 1/2 to the x instead, so we consider this graph, notice how it just gives it almost like a mirror reflection. Actually, it is exactly a mirror reflection across that vertical axis. It has the same basic shape, but it's going the opposite direction. So instead of going from low to high, this one's going from high to low. And you can see, right, we still go through the point 0, 1, as all exponential functions will, unless they get shifted away from that. But you have the point 1, 1/2. You're going to have 2, 1/4 right there. But it is exactly the opposite graph of 2 to the x. So the base does play a major role in determining what the function looks like. When it comes to working with exponential functions algebraically, we have a few laws of exponents that we can use to our advantage. So if a and b are positive, and x and y are any real numbers, then b to the x plus y power is the same thing as b to the x times b to the y. Okay, so adding within the exponents is the same thing as multiplying the bases. I'll go down here, b to the x minus y. It does the same kind of thing, but this one was addition turning into multiplication. For subtraction, that's going to turn into division. So this will be b to the x over b to the y. If you have a power raised to another power, so b to the x raised to the y, you're going to end up multiplying the powers, b to the x times y. Okay, and again, notice the distinction between these two. Okay, so this is a product of two bases that give us a sum in the exponent. This one is a power raised to another power, and that gives us the multiplication up here in the exponent. And then lastly, if you have two bases multiplied, both raised to the same power, you can distribute that power to both. So we would get a to the x times b to the x. So these laws can really help us in solving algebraic problems with exponents, regardless of what the base is. Now, when it comes to graphing and transformations of graphs, we can also apply these to exponential functions. So if we look at this example right here, sketch the graph of y equals 3 minus 2 to the x and determine its domain and range. So the graph that I already have sketched here This is the parent function. So notice our original function would be this 2 to the x right here. So this is 2 to the x that I already have sketched out here. And you can see the behavior. It matches what we had just done when we looked at it on Desmos a couple minutes ago. Now we need to look at what transformations are being performed on it here. So it is being negated. So we have a negative out in front of the 2x, 2 to the x. So we're going to flip vertically. So that's what our minus is going to do. And then we have this 3 out in front. This is the same thing as just having a plus 3. It's just in front of the exponent this time. But that plus 3 just means we're going to shift up 3 units. So we're going to take this graph. We're going to flip it across the x-axis, so flip it vertically. So let me just get a couple kind of points on here. Some of the major ones. And it is asymptotic, so it will never hit that x-axis. And there we go. It's going to grow downward forever. So that's the vertical flip. And then we shift it up 3 units to get the final version of this graph. So the asymptote is no longer here at 0. It's up at 3. So we'll go ahead and put that asymptote in right there. And then if we plotted any points along the way, you can kind of hold on to those points. Right there. Right there. And right there. And I'll go ahead and do this one as a solid curve, since this is our final answer. Okay, and it's going to get really close to the one in purple, but it'll never actually reach it. They'll just run kind of alongside each other forever. Okay, but that is the final version of this graph. So this one, this is 3 minus 2 to the x. And the domain and range, well, for the domain, we're looking for all possible inputs. So every possible x value that could go into this function. There are no restrictions. It can go all the way from negative infinity all the way out to positive infinity. So that's going to be all real numbers, or in interval notation, negative infinity to infinity. The range, on the other hand, is restricted. It can go all the way down to negative infinity. However, it has this asymptote right here. It cannot go above that line. That line is at 3. So our range is going to be negative infinity up to 3. And because we're not including 3, it gets parentheses instead of square brackets. And those are the domain and range for this transformed function. Now, an important exponential function for us to talk about here is the natural exponential function. So this is involving what we call the number e. So e to the x. This is our natural exponential function. E itself is an irrational number. It's about 2.718, etc. But this number comes up so frequently in natural calculations, in just the natural world, that it does get its own special name. And we will be using e very frequently in calculus, and you'll see why as we get a little further along in the class, but there are a lot of nice features that come along with this function as opposed to some other exponential functions we might work with. So we like to use e to the x very frequently. In terms of its graph, so e itself is somewhere between 2 and 3, but a little bit closer to 3. So here's 2 to the x, here's the graph of 3 to the x, and here's the graph of e to the x. So if you look at e to the x right here, you can see it is between 2 and 3, but it does go a little bit closer to 3, right? Because it's about 2.7. But its behavior is exactly the same. So all these exponential functions are behaving the same way. It's just that the steepness and the specific location of this graph depends on the base, which in this case is e. They all go through that point 0, 1, so they all have that in common, but then each one changes individually as you go further along. So that brings us to the end of section 1.4 and our introduction to exponential functions. Now, moving on to section 1.5, we're talking about inverse functions and logarithms. So a function f is what we call one-to-one if it never takes on the same value twice. So in other words, anytime you have two x values that are different from each other, their outputs, f of x1 and f of x2, should be not equal as well. Okay, so again, if you have two x values, so at 1 and at 3, I should have two completely different output values. Now, when we talk about functions, we talk about every input having exactly one output. Well, a one-to-one function, that is still true. It must have only one output for every input, but it must also never repeat outputs. Okay, so that's another way of wording this. So should never repeat outputs. And visually and graphically, it must pass what we call the horizontal line test. So just like the vertical line test, we can use the horizontal line test. So if we have a graph like y equals x cubed, for example, so a graph that looks kind of like this, we know this is a function because it passes the vertical line test, right? You can draw any vertical line you want through it, and it only hits one point. But it also passes the horizontal line test because no matter where we draw a horizontal line, we will only ever hit the graph once. In other words, it only ever hits each output once. Okay? It never repeats outputs. Whereas, if we look at the graph of y equals x squared, so something parabolic like this, and it doesn't take very long to see that we get two outputs for one horizontal line. So this one, even though it is a function, right, because it passes the vertical line test, every input has exactly one output. It's just that every output gets repeated more than once. So while this graph over here, this one is one-to-one. That's my abbreviation, 1-to-1, 1-1. This one over here is not one-to-one. Okay, so again, it still is a function, but it doesn't have this one-to-one relationship. Every one input gives us exactly one output, no repeats. Now, if we know that a function is one-to-one, so let f be one-to-one, then its inverse, written like this, it looks like f to the -1 power. It's not. That's just a notation that we use. Its inverse function is defined saying f inverse of y equals x if and only if f of x equals y. So just a notational piece. That notation in the middle says if and only if. So f inverse of y equals x if and only if f of x equals y. So this is the one that we're used to, but this is an equivalent and also true relationship, assuming that the function is 1 to 1. So and notice what happens here. In the original function, we have f of x equals y. So the inputs are x's, the outputs are y's. In the inverse function, the inputs are y's and the outputs are x's. Basically what the inverse is doing is it's switching everything up. It's switching the roles of input and output. It's switching the roles of x and y. And that can be seen in its domain and range as well. The domain of f inverse is the range of the original, and the domain of the original is the range of f inverse. And again, the original, the domains are the x's. In the inverse, the range are the x's, right? Or I guess that's this one here. In the original, the outputs are y's, so the range are y's. In this one, the inputs are y's, so the domain are y's. So everything is just kind of flipped. Everything is opposite. It has switched places with each other. The inverse of a function can be applied to a function, and they can, what we say, undo each other. So if you take f of x and then you run that through the inverse function, they will end up essentially canceling each other out. They will undo each other's effects, and you'll be left with just an x. Similarly, if you take the inverse function and run it through the original, you will be left with just an x. And that's the whole point. Because they're inverses, they work exactly opposite each other. They work to undo each other. Now, how do we find the inverse if we're given a function? Well, first, we're going to set up y equals f of x. So we're going to write everything out in its proper form. And we're going to, since we're switching around what we're looking for, in this case, right, y equals f of x. In this one, x equals f of y, f inverse of y. So we're solving for x in this case. Solve for x in terms of y, if possible. And once everything is said and done, you will have, x is f inverse of y, like this. And then notationally, we like to switch it back so that the x is on the inside and the y is on the outside. So we'll interchange x and y at that point. That's not doing the same thing as just taking the inverse. Taking the inverse doesn't just mean like we can just switch the letters back and forth arbitrarily. It's more for notational purposes because you've created a new function now when you take the inverse. And so we like x to be on the inside. So we'll switch, we'll solve for x in terms of y, and then we just change their labels so that the one on the inside is always called x and the one on the outside is always called y. You might have been taught to switch the variables first and then just solve for the y. That's the same thing. It's totally equivalent to that process. It is the same. For example, if we want to find the inverse of f of x equals x cubed plus 2, we'll go ahead and put that as a y equals x cubed plus 2. And let's solve for x. So we're going to subtract the 2. We need to get an x by itself, so we're going to take the cube root to undo that cube. So we're going to have x equals the cube root of y minus 2. Now we've solved for x, and now notationally, we're going to go ahead and just switch their labels now so that we can say that y equals the cube root of x minus 2. And then we'll go ahead and rewrite using the inverse notation. So in other words, f inverse of x is the cube root of x minus 2. And that would be our final version of that answer. Now, in the process of switching these variables, of changing the roles of x and y, we can see the effects on graphs. The graph of f inverse is obtained by reflecting f across the line y equals x. So basically what's happening is all of the x's are becoming y's and the y's are becoming x's. And in doing so, the graph reflects. It flips its position. And we'll see an example of that in just a minute. Now, the most common use of inverse functions for our purposes here is going to be logarithmic functions or log functions. Log functions are the inverse of an exponential function. So we say log base b of x equals y if and only if b to the y equals x. So these are two equivalent statements. So this one, of course, is the one we're kind of used to, the exponential form, but they are exactly equivalent to each other. A log is a way that we have to undo the effects of an exponent. So this allows cancellation as follows. So if you take log base b of b to the x, they essentially undo each other's effects, and you're just left with the x. And then b raised to the log of b, they undo each other, and you're just left with the x again. And just to show the effect graphically, here's the graph of 2 to the x again. Here's the graph of log base 2 of x. And you can see if I just put in the line y equals x, you can see, of course, that it is a mirror image. It is a reflection across this center line. So you've got the point 0, 1 here. Over on this side, you have the point 1, 0. So the x's and y's have flipped. They have swapped roles. Right? Over here, the x input was 0, the output y was 1. Over here, the input x is 1, the output y is 0, etc., all the way down both of these graphs. So this is what an inverse relationship looks like for two functions. In this specific case, for exponential functions in red and logarithmic functions in the purple. Now, just like the laws of exponents, there are also laws of logarithms that we can apply. They're derived essentially the same way, just using the inverse properties. So if we have log base b of x times y, well, remember how it was before with multiplication and addition. This will become log base b of x plus log base b of y. And similarly, if you have log base b of x over y, remember the division before was related to subtraction. This will become log base b of x minus log base b of y. And this one, if you have log base b of x to the r, remember before when you had a power raised to a power, it turned into multiplication. This one does something very similar. You have a power here. It's going to become r times log base b of x. This one will come in very handy. We'll use this one pretty frequently. But basically it allows you to bring that power down to the front of the logarithm. So these are the logarithm laws. Now, we talked about the natural exponential function in the previous section. There is also a natural logarithm. This is logarithm with the base of the natural exponential function e. So it's log base e, but we use it so frequently that it gets its own name, and that is ln of x. ln of x, so natural log. So ln of x is the natural logarithm that's log base e, and it obeys all the same log properties. It behaves the same way as other logarithmic functions. It just has e as its base. So a thing to note here, if we take ln of e, that's the same thing as log base e of e to the first. So these two would undo each other, and we would be left with just 1. So ln of e is 1. This will be a helpful property as we're solving problems using exponential and logarithmic functions. Speaking of which, let's go ahead and solve this equation. Solve e to the 5 minus 3x equals 10. So we're trying to find the value of x. Now, this is where logarithms can help us a great deal when we're solving problems, because this x is now currently trapped inside the power of this e, and there's no way to get it out using just our standard algebraic techniques. What we need to do is we need to utilize log properties. So what we're going to do is I want to be able to get this down out of the power and get rid of that e. So I'm going to take the natural log of both sides. So we're going to get ln of e to the 5 minus 3x. And whatever you do to one side, you have to do to the other to keep it balanced. So that's equal to ln of 10. And now we can use that log property. Look at the third one that said you can bring powers down to the front. So we're going to bring that whole thing down. 5 minus 3x ln of e equals ln of 10. Now ln of e is 1. We just talked about that up here. So really, this is just 5 minus 3x equals ln of 10. So we can go ahead and subtract that 5 over. So negative 3x equals ln of 10 minus 5. And then we go ahead and divide both sides by the negative 3. So let me go ahead and move that negative in and flip these around. So that's going to be 5 minus ln of 10 all over 3. And that's going to be our exact value for x. So again, this is our exact value. And if you're doing problems where they just want you to round or to approximate the value using a decimal, you would just punch this into a calculator. There is a natural log button on the calculator. But for our purposes, again, most of the time, unless it asks you to specifically round or approximate, you want to leave the exact answer as much as possible. But this is how we can use logarithms to help solve exponential problems and exponential equations. The other major type of inverse function that we need to talk about are inverse trig functions. Inverse trig functions use the same notation, that -1 notation, or they use an arc notation. So arc sine, arc cosine, and arc tangent. These are equivalent to these versions of their equations, and they do have restricted domains. So you can see here, these domains are all limited because they're acting in reverse, basically, right? The inputs and outputs are flipping, they're switching position. So the outputs were restricted before, now the inputs are being restricted so that we don't have any unnecessary overlap, not repeating values, which would make it not a function anymore. But when we're talking about inverse trig functions, we're looking at, again, going backwards, going the opposite direction. So before we would say, you know, what is sine of pi over 2 or something like that, and we would get out a number. So in this case, that'd be 1. But in this case, we're saying what is sine inverse of this coordinate number, and we're trying to get out the angle that corresponds to that. So like this question here, instead of sine of an angle, it's sine inverse of the output value. So this is really asking what angle has a sine value of 1/2. And as with everything on like the unit circle, there would be more than one, except we are restricting our domain to only lie, in this case, between -pi over 2 and pi over 2, so that we don't have repeated outputs, and that would make this not a function anymore. So the question, what angle has a sine value of 1/2, specifically one that falls within this range? And there is only one that meets that criteria, and that's pi over 6. So, and again, the alternative version of this question, sine of pi over 6 is 1/2. And these trig functions and inverse trig functions can undo each other. However, you have to match. So like for this part B here, this isn't sine of inverse sine, it's sine of inverse cosine. So we need to use them, do them separately here. So inverse cosine of 1/2. That's asking the question, what angle produces a cosine value of 1/2? And the answer to that is pi over 3. So this question now becomes sine of pi over 3. And sine of pi over 3, that is just going in the normal kind of straightforward direction that we're used to. That's radical 3 over 2. All right, and that brings us to the end of section 1.5, dealing with inverse functions and logarithms.